Hey guys, we'll continue off where we left off, talking about open addressing. Last things that we talked about was hash insert and how the function works. By using a hash function h given the key k, we can take an index I to search for any open slot in a certain hash table. And we relatively just iterate through the whole thing until we find an open slot. And once we find an open slot, then we take that slot and fill it in. If there's no open slots available, we throw the error hash table overflow, and this happens when I equals to m. We also have another function in this hash search, hash sort of open addressing, which is hash search, and it takes two arguments. It takes the table itself, as well as key k. Returning j, it finds a slot j, which contains a key k or nil if it is in presence. So here we start the iteration process setting I equal to 0. Then we do set the repeat function. And until t of j equals nil or I equals n. Since we search the whole table, or we go through the table until we find a blank slot, knowing that all their slots underneath will be blank. Since I believe in this format that they've done, most slots in a table will be filled at the top and at the bottom will be empty in this sort of scenario. Deletion from an open address hash table is quite difficult. We delete a key from slot I. We simply cannot mark the slot as empty by storing nil in it. Exactly because, of course, it has that same order. If we did, it might be unable to retrieve a key K whose insertion we had probed slot I and found it occupied. We can solve this problem by marking the slot and special value deleted instead of nil. And we can modify the hash table insert to treat as if it were empty so we can put in a value. However, we don't have to modify the hash search. So simply by instead of saying nil in the space, we can save it as deleted, which makes it so that we're able to mark it in terms of the hash table to be still able to be filled by other functions. When we use a special value deleted, however, search time no longer depends on the load factor A, and for this reason, chaining is more commonly selected as a collision resolution when keys must be deleted, if that makes sense. Okay, in our analysis, we assume uniform hashing. That is, the probe sequence of each key is likely to be any of m factorial permutations between 0 and m minus 1 in that set. Uniform hashing generalizes the notion of simple uniform hashing. Let's just go through that again. If we were to review uniform hashing, we went through universal hashing, I think, for the first time going through uniform hashing. There are two different terms. I'm sitting right on top of the AirNet, which is kind of annoying, not gonna lie. Here, this should be better. The probe sequence of each key k is likely to be any of m factorial permutations. Uniform hashing generalizes the notation or notion of simple uniform hashing defined earlier to a hash function. It produces not just a single number, but a whole probe of sequences. True uniform hashing is difficult to implement, however, in practice suitable approximations such as double hashing defined below. So I don't really understand this, so I'm going to mark this down as one term I should review later. Now this is your atomic. This is page 271, and I'll come back to you guys. I'm just making this list. Universal hashing. And I promise you guys that uniform, not universal. I'm so used to seeing universal because we talked about that. Uniform. And I'll figure out completely how this works, and I'll get back to you on that. Okay. So Let's start with linear probing then, okay? Given an ordinary hash function h prime and the universal set between 0 to n1, we're given as an auxiliary hash function, and the method of linear probing uses the hash function in terms of h prime of k plus some index I, and we mod that by m for the m slots. And for I equal to any of these numbers in the set, given key k, we first probe t in the table hk, h prime k, which is a slot given by the auxiliary hash function. Which is the slot given by the auxiliary hash function. And next we probe slot h prime of k plus 1 in terms of t, and so on to the slot t m minus 1. Then we wrap around the slots around to slots T0, T1 until we finally probe the slot, because the initial probe determines the entire probe sequence. There are only m distinct probe sequences here found. Okay, linear probing is easier to implement, but it suffers from a problem known specifically as primary clustering. Long runs of unoccupied slots build up increasing average search time. Clusters arise because an empty slot received by I, full slots get filled. Next, with probability I plus 1 divided by n. Long runs of unoccupied slots tend to get longer, and the average search time increases, unfortunately. Move away from this. I don't know if you can actually hear me. I think it's a chiller. Let's see where Sakshi went. Let's see if you message me something. That my friend. Sorry, guys. See, my friend's going on vacation. Long runs of unoccupied slots tend to get longer. Interesting. This is very cool. I also don't get any of this, so maybe I should just write page 272 as well. And I think, honestly, all these are the same sort of topics. There's a lot of math here as well. I think 272, to when you get the perfect hashing, is when I should do this stuff. 277. Okay. 272 to 277. Okay. Perfect hashing. Although hashing is often a good choice for its excellent average case performance, hashing can also provide excellent worst case performance. That makes sense. Performance when the set of keys is static. Once the keys are stored in the table, the set of keys never change. Some applications naturally have a set of static keys, which is considered to be reserved in words of programming language, or the set name of CD-ROM on some computers, if you remember that. So we call a hashing function perfect hashing if all of one memory accesses are required to perform the search in the worst case. If that makes sense. So let's just go through it again. So when keys are static, that means they don't change. Once they're stored in the table, the set of keys never change. And this is usually done in some programming language with set of very reserved keywords, or the set of file names on a CD-ROM. And this technique is called perfect hashing in specific and is O1 and memory. So to create a perfect Marlon, Marlon. Oops, oops, oops. That was my cat. So I don't understand this at all. I can try to understand it. Let's try to understand it. Okay. Using perfect hashing to store set k, outer flash function h of k is AKB mod. So actually, this is not making sense. So I'm going to start listening to some videos, see if it makes sense, and I'll catch you later, guys. See ya.